December 7, 1941, 7:55 a.m. The first wave of Nakajima B5N Kate bombers screams over Oahu's mountains like mechanical locusts, their engines drowning out the Sunday morning calm that millions of Americans will remember as the last moment when their country felt safely distant from a world at war. At Wheeler Field, 18 miles northwest of Pearl Harbor, Technical Sergeant Mike O'Brien watches Japanese Zero fighters strafe the flight line with methodical precision, transforming rows of parked P-40 Warhawks from America's premier fighter aircraft into twisted sculptures of aluminum and steel, aviation gasoline, and shattered dreams. The attack lasts 110 minutes. When the smoke clears and the enemy formations disappear toward the northwest horizon, Wheeler Field looks like a graveyard for metal eagles. 42 P-40s destroyed outright. 17 more damaged beyond what initial assessment considers economical repair. And one particular Warhawk, tail number 41-13297, that every expert who examines it declares totally beyond salvage, a complete loss, suitable only for scrap metal recovery and spare parts cannibalization to support aircraft that might actually fly again someday. But Mike O'Brien sees something different when he crawls through the wreckage of 41-13297. Not destruction, but transformation. Not failure, but opportunity disguised as catastrophe. The Japanese strafing runs that should have killed this fighter completely have instead created a unique combination of damage and survival, destruction and possibility that might, just might, allow for the kind of creative reconstruction that turns disasters into triumphs if someone possesses sufficient imagination, technical skill, and stubborn refusal to accept expert opinion about what is and isn't possible when survival depends on making broken things work again. He pulls out his inspection tools and begins documenting damage that the manual says requires total aircraft replacement. Cataloging destruction that regulation demands he report as irreparable loss. Calculating repair requirements that exceed every standard protocol for field maintenance operations. But Mike understands that standard protocols assume peacetime conditions, adequate replacement aircraft, and the luxury of following proper procedures when proper procedures are designed for circumstances that no longer exist. After enemy action transforms military aviation from training exercise into survival necessity. This is Pearl Harbor plus 6 hours. The United States of America has been at war for exactly 355 minutes. Thrust from isolationist neutrality into global conflict by an attack that demonstrated how quickly distance becomes irrelevant when enemies possess sufficient motivation and technological capability to project power across oceans that Americans assumed provided natural protection from foreign aggression. The Pacific Fleet burns in Pearl Harbor. Army Air Force's installations across Oahu smolder under columns of black smoke that mark the funeral pyres of American military aviation's peacetime assumptions about invulnerability and preparedness. At Wheeler Field, the damage assessment reveals the particular kind of destruction that creates maximum psychological impact with strategic efficiency. The Japanese attack focused on aircraft rather than infrastructure, on destroying American air power rather than occupying territory, on eliminating defensive capability rather than seizing ground that would require long-term occupation and defense. Hangars remain largely intact, but aircraft lie scattered across the tarmac like broken toys, their aluminum skins punctured by 7.7mm machine gun rounds, their fuel tanks ruptured by 20mm cannon fire, their engines and propellers twisted into abstract sculptures by the kinetic energy of high-velocity projectiles designed specifically to destroy rather than disable military aviation assets. The official assessment process moves with bureaucratic efficiency through the wreckage, categorizing damage according to established criteria that distinguish between aircraft requiring minor repair, major overhaul, or total replacement. The system works well for peacetime maintenance schedules and normal operational wear, but it proves inadequate for combat damage that creates destruction patterns outside normal experience. It combines multiple failure modes in ways that standard repair procedures never anticipated because they assumed predictable damage progression rather than the random violence that enemy action produces. P-40 Warhawk 41-13297 falls into the total replacement category according to every official assessment criterion. The port wing has been nearly severed by cannon fire, hanging from the fuselage by structural members that should have failed completely, but somehow maintained minimal connection through what can only be described as metallurgical accident. The engine has taken multiple machine gun hits that punctured cylinder heads, destroyed spark plug connections, and filled the oil system with metal. Fragments that should have seized the power plant immediately, but left it frozen in a state between function and failure that creates unique opportunities for creative repair approaches. The cockpit canopy has been shattered by explosive rounds that somehow missed the pilot's seat by inches, creating a spiderweb of fractured plexiglass that obscures vision but maintains structural integrity in ways that suggest the possibility of temporary repair rather than complete replacement. The main landing gear absorbed impacts that bent struts and cracked attachment points, but the damage follows stress patterns that might respond to field straightening techniques if someone possessed the imagination to see alignment possibilities where regulations see only replacement requirements. But Mike O'Brien possesses exactly that kind of imagination. 23 years of aircraft maintenance experience, from barnstorming biplanes through modern military fighters, has taught him to read aircraft damage like medical doctors read symptoms, to understand that apparent destruction often masks recoverable functionality. The creative repair can restore capability that replacement procedures assume has been permanently eliminated. He looks at 41-13297 and sees not total loss, but complex puzzle, not irreparable damage but challenging reconstruction project that might produce a functional fighter if approached with sufficient technical creativity and willingness to violate standard procedures in service of extraordinary objectives. The decision to attempt resurrection comes not from official authorization, but from personal conviction that extraordinary circumstances require extraordinary responses, that wartime conditions justify risks that peacetime regulations prohibit, that survival sometimes depends on the willingness to ignore expert opinion about what is and isn't possible when national defense requires maximum utilization of available resources. Regardless of theoretical limitations, Mike understands that every aircraft restored to service multiplies American defensive capability, that every fighter returned to combat status represents tactical advantage that might determine whether additional enemy attacks succeed or fail. The reconstruction begins with systematic disassembly of damaged components, careful documentation of destruction patterns, methodical analysis of what can be repaired versus what must be replaced, using salvaged parts from other damaged aircraft that possess complementary damage profiles. Mike approaches 41-13297 like an archaeologist reconstructing ancient artifacts from scattered fragments, identifying pieces that retain functionality, understanding how undamaged components might be recombined to create whole systems from partial survivals. The port wing presents the most obvious challenge. Standard procedures require complete replacement when structural damage exceeds specific tolerance limits. But Mike recognizes that the cannon rounds that nearly severed the wing also relieved stress concentrations that might have caused catastrophic failure under normal flight loads. The accidental stress relief, combined with creative reinforcement using structural elements salvaged from other damaged aircraft, might actually produce a wing that performs better under combat conditions than original factory specifications intended. The engine reconstruction requires techniques that violate multiple maintenance regulations but might restore power plant functionality if theoretical principles prove applicable to practical repair challenges. Mike begins by completely disassembling the Allison V1710 engine, cataloging damage to individual components, identifying which cylinder heads can be repaired, which pistons retain adequate compression capability, which crankshaft bearing surfaces remain within acceptable tolerance limits despite impact damage that should have destroyed dimensional accuracy completely. The process reveals that much of the apparent engine damage affects secondary systems rather than primary mechanical components, that careful cleaning and precision measurement demonstrate functionality, where visual inspection suggested total destruction. The machine gun rounds that seemed to have destroyed the power plant actually created access routes for repair procedures that normal disassembly wouldn't allow, enabling replacement of damaged components that peacetime maintenance schedules would never access without complete engine overhaul. Working 18-hour days in a maintenance hangar that lacks proper equipment for major reconstruction projects, Mike employs field-expedient techniques that combine formal training with improvised solutions, official procedures with creative alternatives that exist nowhere in technical manuals but prove effective when tested against practical requirements rather than theoretical specifications. He fabricates replacement parts using materials salvaged from aircraft too damaged for any reconstruction attempt, creates tools from scrap metal and discarded equipment, develops techniques that will influence military maintenance procedures for decades, but begin as desperate expedients motivated by immediate necessity rather than long-term planning. The wing repair requires structural welding that exceeds Mike's formal certification, but falls within his practical capabilities developed through years of unauthorized experimentation with metallurgical techniques that official training programs discourage because they involve risks that peacetime safety considerations prohibit. But wartime changes the mathematics of acceptable risk considerably, especially when the alternative to risky repair is certain loss of military equipment that enemy action has made irreplaceable through normal supply channels. Each welding operation could weaken the wing structure catastrophically if performed incorrectly, could create stress concentrations that cause in-flight failure, could compromise aircraft safety in ways that threaten pilot survival and mission success. But Mike understands that perfection is the enemy of adequacy when survival depends on getting aircraft functional rather than optimal, when the choice is between risky repair and certain loss of defensive capability that might determine whether additional enemy attacks succeed against inadequately defended targets. The breakthrough comes when Mike realizes that the combination of battle, damage, and creative repair has accidentally created what amounts to a field modification that improves aircraft performance in ways that original design specifications never anticipated. The stress relief created by cannon damage, when properly reinforced with salvaged structural elements, actually reduces wing flutter characteristics that limit high-speed performance in standard P-40 configurations. The engine modifications forced by combat damage elimination of sophisticated control systems create simplified power plant operation that proves more reliable under combat stress than factory specifications intended. 3 weeks after the Pearl Harbor attack, when most experts assume that 41-13297 will never fly again, Mike completes reconstruction efforts that transform total loss into functional fighter aircraft through techniques that exist nowhere in official maintenance procedures but prove effective when tested against practical requirements rather than theoretical limitations. The resurrected P-40 incorporates field modifications that violate numerous engineering specifications but create performance characteristics that exceed original factory standards in several important areas. The test flight happens on January 2, 1942, with Lieutenant Colonel James Davidson piloting an aircraft that every expert predicted would never leave the ground again, evaluating flight characteristics that result from creative reconstruction rather than standard manufacturing processes. The resurrected Warhawk responds to control inputs with precision that surprises everyone familiar with pre-attack performance specifications, demonstrates stability characteristics that seem to improve rather than compromise handling qualities, shows power output that equals or exceeds original engine specifications despite field repair techniques that should have reduced performance significantly. But the real test comes 3 weeks later when Japanese submarines surface off the California coast and launch reconnaissance float planes that penetrate American airspace with the same audacity that characterized the Pearl Harbor attack. The resurrected P-40, now designated Phoenix by pilots who understand its resurrection story, intercepts the enemy reconnaissance mission 20 miles southwest of Los Angeles, engaging Aichi E-13A, Jake float planes in aerial combat that tests every aspect of Mike's field reconstruction work under conditions that reveal whether creative repair produces combat-capable aircraft or dangerous liability. The engagement lasts 11 minutes. When it ends, 2 Japanese reconnaissance aircraft have been destroyed by cannon fire from guns that should have been inoperable, delivered by an aircraft that should have been scrapped, flown by a pilot who understands that he owes his survival to a mechanic who refused to accept expert opinion about what was impossible. The third enemy aircraft escapes with sufficient damage to prevent completion of its reconnaissance mission, returning to its submarine with intelligence gaps that compromise Japanese understanding of American West Coast defensive preparations. The Phoenix returns to base with minor combat damage that proves the structural integrity of Mike's wing repairs, with engine performance that demonstrates the reliability of his power plant reconstruction, with pilot testimony that confirms the aircraft's combat effectiveness despite field modification techniques that exist nowhere in official maintenance procedures. The success validates every regulation violation that Mike employed during reconstruction, justifies every risk he accepted in service of returning destroyed aircraft to combat capability, demonstrates that innovation often requires the willingness to ignore expert opinion about limitations. Word of the successful combat mission spreads through Army Air Force's maintenance communities with the speed that important technical innovations always achieve when they prove applicable to widespread problems that standard procedures handle inadequately. Mike's reconstruction techniques become informal models for field repair operations that face similar challenges, creative approaches that enable recovery of aircraft that standard assessment procedures declare total losses, innovative solutions that multiply available combat capability by refusing to accept expert opinion about what is and isn't repairable under field conditions. Engineering teams begin documenting Mike's field modification techniques, creating formal procedures from improvised solutions, establishing official protocols for reconstruction approaches that began as desperate expedients motivated by immediate necessity rather than long-term planning. The stress relief techniques that seemed like dangerous compromises proved superior to original design specifications under combat loading conditions. The simplified engine controls that resulted from combat damage proved more reliable than sophisticated automation under operational stress that peacetime testing never duplicated. The Phoenix continues combat operations throughout 1942, participating in defensive missions over the American West Coast, engaging enemy submarines and reconnaissance aircraft with success rates that validate every aspect of Mike's reconstruction work. The aircraft accumulates combat flight hours that exceed the operational lifetime of most standard P-40s, demonstrates reliability characteristics that surpass factory specifications, provides evidence that creative reconstruction can produce superior performance through different methods than original manufacturing processes employed. But more importantly, the Phoenix becomes symbol of American determination to recover from devastating surprise attack, to transform destruction into opportunity, to refuse acceptance of defeat when survival requires extraordinary responses to extraordinary challenges. The aircraft that rose from Pearl Harbor wreckage represents national capacity for renewal and innovation, for finding strength in apparent weakness, for converting catastrophic loss into strategic advantage through human ingenuity and stubborn refusal to accept expert opinion about limitations. Other mechanics begin applying Mike's techniques to aircraft damage that standard procedures declare irreparable, expanding the principles he discovered under survival pressure to normal maintenance operations that face resource constraints and equipment shortages. The reconstruction approaches that seemed like desperate expedients prove applicable to peacetime maintenance challenges, providing alternatives when standard repair methods are unavailable or inadequate, demonstrating that innovation often emerges from necessity rather than abundance. The war continues for 3 more years. Mike O'Brien advances through maintenance ranks, eventually supervising reconstruction, operations that restore hundreds of aircraft to combat, capability using techniques that began with one mechanic's refusal to accept expert opinion about a single damaged P-40. His wartime innovations influence post-war aviation maintenance procedures, providing foundation for modern aircraft recovery techniques that enable restoration of functionality where standard assessment declares only total loss. Years later, when aerospace engineers design systems for spacecraft and military aircraft that must operate in environments where replacement parts and expert technical support are unavailable, they study field modification reports from World War II, including Mike's Pearl Harbor reconstruction of electrical and structural systems that should have been impossible to repair outside fully equipped manufacturing facilities. The principles he discovered under combat pressure, that destruction often masks recoverable functionality. The creative repair can exceed original performance specifications. That expert opinion about limitations often reflects psychological rather than physical constraints. These lessons become formal design criteria for systems that must function reliably despite damage, despite operating conditions that exceed normal specifications. The hangar at Wheeler Field, where Mike performed his reconstruction work, remains in use, now housing modern fighter aircraft that incorporate design principles derived from his wartime innovations. Sometimes, when maintenance crews work late shifts repairing complex systems under time pressure, supervisors tell the story of the mechanic who refused to accept that the Eagle couldn't fly again, who proved that human determination can overcome technical limitations when survival depends on finding solutions that exist outside standard procedures and expert opinion about what is possible. The Phoenix itself was eventually lost to normal operational attrition, worn out by combat missions rather than destroyed by enemy action, retired from service when peacetime replacement procedures became available again. But the aircraft's combat record, 49 confirmed aerial victories, including the reconnaissance float planes that marked its return to battle, and dozens of enemy fighters engaged during defensive missions over American territory, validates every regulation violation that Mike employed during reconstruction, justifies every risk he accepted in service of returning destroyed aircraft to combat capability. The 49 victory marks painted on the Phoenix's fuselage represent more than individual combat successes. They symbolize triumph over expert opinion that declared success impossible, victory over regulatory constraints that prohibited the innovation necessary for survival, proof that human ingenuity can overcome any limitation when properly motivated by necessity and supported by willingness to risk failure in service of extraordinary objectives. That's standard. Procedures are designed to prevent rather than enable. In museums across America, restored P-40 Warhawks carry plaques that mention the Phoenix and its resurrection from Pearl Harbor wreckage, reminding visitors that innovation often begins with refusing to accept expert opinion about what is possible, that creativity emerges when normal solutions prove inadequate, that survival sometimes requires techniques that peacetime safety considerations prohibit, but wartime necessity demands. The story continues to inspire maintenance crews who face similar challenges with different equipment, who must restore functionality where standard assessment sees only replacement requirements. If stories like this remind you that eagles can always fly again when human determination refuses to accept defeat, that innovation emerges from necessity when survival depends on finding solutions outside normal procedures, then perhaps there are other moments when rejecting expert opinion about limitations created breakthroughs that changed how we understand what human ingenuity can accomplish when motivated by circumstances that demand Extraordinary responses to extraordinary challenges, that's standard. Solutions cannot address adequately.